the relations or their applications in quantum information and communication side. So am I audible and the board is visible, right, sir? Everything is fine?
Yes, sir. Clear.
Yeah.
No problem.
Thank you. So, although we shared some notes on basic probability and statistics, and I'll request that you please go through if you have haven't covered in your UG or previously. That will be helpful. Otherwise, these are very simple and basic topics. Assume this prerequisite, right? And we are covering today mostly the quantum information theoretic part. So today I'll be in my lecture. There will be two part. One on the quantum information side, where yesterday we were talking about noise, and today we'll deal with quantum noise, right? With more details. And when I say quantum noise, right? Of course, how to analyze the noise, right? So that part, analysis part. So this is the first part of the today's class. Second part, I'll talk about one communication protocol that is called quantum teleportation. Quantum teleportation, the basic principle, how it works using linear algebraic and probabilistic approach. Plus, we'll do a Qiskit implementation of quantum teleportation. So I hope you must carry one laptop or computer with you in the like around the class is starting at 2, right? So around 4 we'll start this Qiskit implementation part in the last hour, and you may need a laptop or a computer. And for today's class, I'll take some slides from our IBM members like the Zlatko Minev and others. So those are the best contents, I believe, and so I'll carry some of the contents which can be shared, right? So yesterday we were talking about the coherent noise, right? The coherent noise. So that typically causes your the over rotation or under rotation, right? So the rotational error. And if you can model this error, you can eliminate simply by matrix inversion techniques, right? Say, for example, if you have X tilde approximate or noisy gate, right, which has a X part and which has an actual part, right? And that basically theta, there is a over or under rotation of epsilon amount, and that is coming as in multiplicative gate operations, right? So that we have seen yesterday's class, and today we'll talk more on other noise, especially the incoherent noise. Then the projection and measurement, basically coming from the measurement part. Measurement noise, right? So this kind of noise analysis are important, and why I'm covering this part, because we need to study the probability statistics, and they have the direct match with the syllabus, right? And how to mitigate this part. So one part of the mitigation techniques that already Dr. Ritojit covered and showed real demonstration, right? And other part is the error correction part, which is beyond the syllabus, right? But we'll come back to error correction a bit in QT6, and we'll go detailed with the quantum communication in QT6. Okay. So there is a direct, those who are attending this QT3 and 4, they can just directly start from end of today's class to directly QT06. Okay. Okay, let's start with certain first nomenclature thing, and then we'll see some more thing. So first is the connectivity part. So quantum and classical interface. Quantum to classical interface. So when we prepare a quantum state, right? Say for example, we prepare a state square root half of a square root the 0 plus 1 state, right? Something like, which is a superposition state. Also, this is known as plus state. Okay. Suppose you have a plus state or a superposition state, we typically denote by a single wiring for the quantum information part with a single wire line. And this is a measurement apparatus. The measurement symbol looks like this. Okay, and before the measurement, this part is quantum. Once we measure the information, we represent by two wire convention. There are two wires, right? This is the representative for classical information in a circuit. And once we measure the classical informations, you typically get either 0 or 1, right? So it means when you measure, so you represent your information in the computational basis 0 and 1 or standard basis 0 and 1. Either you see this one or you see this one, right? Now, if you read this experiment multiple times, a capital M number of times, you repeat this experiments, which is called quantum sorts. Okay. Which is called quantum sorts in Qiskit. So, and you see that this is coming, say, n1 times, and this is coming as n2 times. So the probability of getting this gate 0, right, is n1 out of m experiment, and probability of getting 1 is n2 times by m experiment, right? And if these are the only two outcomes that you expect, then the sum of these two probability, that is n1 plus n2 by m, should be equals to 1, right? And that's how you see the histogram, right? So in the computational basis 0 or 1, you see certain probability, right? Whether it is half and half or approximately close to half, right? Due to noise, it won't be half. So that we have seen yesterday, amplitude damping and other cases like coherent noise cases, and we'll see today more such cases and their implications. So so this side, you have the information Kate psi, which is a complex vector, right, and belongs to the Hilbert space. And this side you have a binary string, right, which is a 0 1 string that you see on your classical laptop, right, normal computer or laptop, right. And this side you have a chamber where there is a processor, so many wires, and it's set up under a cryo setup, right. So this is your room temperature machine, right. So after the measurement, you retrieve the information using classical wires, right. Now next is so we also we also have seen the resolution of the identity, right? So that means if I start with a quantum state psi and I do measurement, right? And the classical result, depending on how many standard basis I have taken, right? It's only 0 or 1, or it's 0 0 2 up to 1 1, or it's depending on number of qubits, how many qubits you have taken. So that many possible types of output it can have, right? So which you can denote with a random variable x, right? So random variable, the after the measurement, whatever you get, so there is an uncertainty of the outcome. That's why you define a random variable x, right? And if there is only two possibilities, 0 and 1, right? So the probability that x equals to 0 plus the probability of x equals to 1, that should be equals to 1, which is the resolution of the identity, right? And this is true for more number of random variables, right? So if the outcome x is 0, right? So the probability of x, how we calculate it? We calculate it as the projection of this 0 and psi state and square, right? And similarly, for x equals to 1, the probability of x equals to 1 equals to 1 inner product with psi, right, square. This is how we calculated the probability, right? This is simply mathematical projections, right? And this projection also create a quantum noise will come. This is also a source of noise. Okay. So now in school you can give it an exercise. You can ask for proof that this is equals to 1, right? So then it's to apply the projections, right? So like this 0 psi square plus this 1 psi square, right? And basically breaking this psi into psi as a state, right? So this can be written as this way also. This psi can be taken outside, and this is right. So this is just you have broken the equations, right? And then this is your simply identity operator, right? Yesterday we have seen this 0, 0 and 1, 1 thing, right? So 0, 0 is basically ket 0 is what? Ket 0 is basically 0, 1, 0, right? 1 and 0. And bra 0 is basically 1 and 0. And if you multiply, you will create a matrix 1 all 0, and similarly all 0 1 for this 1 1 matrix, right? So it's something like this. This is for this matrix, and this is a called projector. Okay, projector, measurement projector. Similarly, P2 projector equals to your 0 0 0 1, right? And if you sum them up, it gives you the identity matrix, right? So this is a different way to look at the measurement operator, right? And this is just simply psi identity matrix times psi, and this is psi square, right? There is a mistake. So this is simply psi square, right? That is equals to 1, right? So will come this picture if you have if you visit to this QT series in YouTube channel, also available my website. I'll share the link. The detailed of various projective measurement is given, right? Various projective measurement and how to design the measurement operator, right? So sum of all the projector should be equals to identity matrix, right? Okay. These are some projectors, say pi 0 and pi 1 in this for the single qubit case. Now, let us dig more. So now let's talk about the expectation value calculation. So because my outcome is I started with psi quantum state, and once I do the measurement, right, I get a random variable x, right? And set of possible outcomes is 0 and 1. It can be more than like single qubit. It can be multiple qubits. So it can be 0 0 0 1 1 0 1 1. And so x belongs to this psi. X can take any value in between 0 and 1, right? So so various measurement operators, let's take, suppose x has the measurement operator, suppose mu x gives x, and 0 is given by mu 0, which is basically this is the projector which help us to get the outcome at 0th basis. That means if your qubit is alpha ket 0, right, plus beta ket 1, right? So so if you simply project this with this projector, right, so you simply multiply this 0 0 projector with the psi state, you will simply get alpha back, right? This is equivalent to the dot product with the 0th state, right? So so basically you get the 0th basis using this mu hat O, this projector, and similarly we get 1 mu hat 1 equals to 1 1 projector, right? So the probability of getting x equals to any random variable, capital X equals to any possible value little x, which is equals to the expectation value of mu hat x, right? And we'll see example to understand this with more clarity. Okay, so suppose how we define the classical expectation, for example. Classical expectation for a discrete random variable. Okay, discrete random variable. So expectation of a random variable x is defined as the summation of the variable x, x times the probability of x equals to x, right? So how to remember? Variable times the PMF, right? PMF, and for all possibilities, PMF of xi, right? Sum of all I, right? That will give you the expectation mu, right? That is the definition of the expectation. There is a question. Can you please explain example of classical state versus quantum state? Uh, Classical state and quantum, so we studied this in detail, right? Uh, so so classical state can be any binary string, right? 0, 1, or anything, right? For the quantum state, you need to prepare a unit vector, right? So that should be norm of this should be equals to 1, and the element any element vi which belongs to the vector v should be a complex numbers, right? So these are the two criteria for the quantum state, right? And it obeys all the postulates of quantum mechanics, right? And they are the vector quantities, right? Complex vector quantities. Now, this is a smaller set. The quantum states are a smaller subset of the classical state, you can say. But in general, they have more properties, and some properties, especially entanglement and all, has very different nature than the classical counterpart. There is one question. Lightning strikes the classical state. I don't know what is lightning strikes and all, but if you can represent in the complex vector unit vector representation of the phenomena you are saying, that's okay. You can represent that quantum state. It's not how you call a particular phenomena, but how you define a particular phenomena in a mathematical way, right? So okay. So in this particular case, right? Suppose I say that the outcome of the zero is suppose has the probability p, right? And the failure probability is 1 minus p in this. So so in this particular case, x can take values 0 and 1, right? So 0 into the probability x equals to 0 plus 1 into the probability x equals to 1, right? So this part becomes 0 and this part only probability of x equals to 1. Suppose in a quantum experiment, earlier we are defining this part like n2 by m, and suppose this is equals to p. So this is equals to the probability p. Okay, for multiple run. Now in terms of quantum operators, we can define terms of quantum operators. So physicists, to answer you, sir, to physicists have very compact definition or very strict definition of the quantum phenomena, right? To mathematician or the computer scientist, these are simple mathematical objects which obey certain mathematical postulates or the properties of a vectors or matrix or mathematical object or group or ring, which kind of property it holds. And accordingly, we say whether it's a classical or quantum state, right? But of course, it might have a very different physical meaning and all in the physics. That might be a different case. Okay, so in terms of quantum operators, we define in this way that expectation of the random variable x is basically x into the probability x equals to x. This is the simple definition where x can take binary values 0 and 1, or it can take a string of zeros and 1, right, for more qubits. So then this is same as x into the expectation of mu hat x, right? And this is like, so over x, little x, and this you can also write as this over little x sum over x mu x. This is absorbed inside, um, because the classical expectation value gives us the expectation value of the quantum operator. M had, if it is a quantum operator is M, then M had is the expectation value of the quantum operator, which is basically X into mu X hat. Okay. For example, 0 into 0, 0, right, was one measurement operator plus 1 into Ket1, Ket1. This is another projective operator, right, which is equals to 0, 0, 0, 1. This is one particular expectation value of a measurement operator, right? So this is in general written as summation over x, x mu x, and in short it is written as simply in Qiskit you will see something like this, very simple notation. This is equivalent. This is just given a so what is the meaning of this? Meaning is that given operator, given an observable, you can say observable or operator M, right? M, right? And a particular state and a state and a state, and that particular state is here is a random variable, right? X, right? So what is the expectation value? What is the expectation value? So this is a very simple way of writing this thing. Yeah. So yeah, I'll share the link towards the end of the session. Okay. Now let's talk about the variance. Why I am covering these things? These are very standard notation used in all quantum mechanics books, quantum computing books, right? I'm trying to relate the classical to quantum because classical part we already know, and there might be sometimes confusion. So just clarity for clarity, right? What is the meaning of expectation values? Expectation is if you have a statistical quantity, right? How you basically measure, right? Measure or how you find a resolution of uncertainty, right? To find the resolution of uncertainty, we define very statistical definitions, right? Suppose, for example, in a classroom, there are many students and they have very different heights, right? It's difficult to say what is the like a particular height of a student in a class, right? So if it is say 10 lakh student, right, and you randomly call a particular candidate, right? So better if there are lots of uncertain in the data sets, you define various measures. Expectation is one of the measure, right? So it's like average, not the average always is how you define it because it depends on the probability mass function. So it's how it's a like a overall representation of the system. Like this is the average height of the classroom or average age group of a particular classroom, right? And similarly, variance part, okay, how the average deviates from the extreme cases, right? Yeah, similarly, basically, when you get the probabilistic outcome from the quantum measurement, right, and given a particular measurement operator, and you repeat the quantum experiment, right? So, what is the expected outcome from the quantum experiment given a particular quantum operator, right? So that means what the expectation means is that if you have a quantum state this, right, and you define pi 0 equals to say 0, 0, right? And every time I have a quantum circuit here, right? And whatever I'm, suppose this is my initial state, right, in it, and this is my final state after the application of the quantum circuit. This is my final state, right? And there might be a lot of uncertainties how we applied, implemented the algorithm, how I applied the U and all, right? So it is not obvious that I will always get 0 or 1, right? So what I do, I force this system every time, right? Basically, suppose this is my pi 0, so I always apply the pi 0 with the size state, and every time I retrieve a result, right? So suppose first time I get something, say A1, second time get A2. So how many times I get the Ket 0, right? Outcome by applying these things. So I count how many times I get the Ket 0. Suppose this is N1 times, then I can say after n trial I get N1 times is the probability P1, right? So this is like how I get the probability from this. Similarly, expectation value is basically you know the probability mass function in general, right? And then you say, okay, if this is the PMF, and then what is the expected outcome if I just use this particular operator, right? I mean, there are various ways how you can define, but this is just if you have a particular measurement operator or particular observable M, right? And you have a random variable X, then what is the expected outcome, given that you know some probability mass function of this X, right? Precisely. Then, so how we define the variance? V of X is basically, classically it is expectation of X square minus expectation of X square, right? So that means this is equals to also the X minus E of X square, right? E of X then whole square, right? So individually, how they are deviated from the first moment, right? So basically, for a quantum part, in this particular case, like this quantum state has only two possibilities, alpha 0 and beta 1, right? And getting the probability of 1 over M experiment, suppose the probability is P, that we have just seen, right? So now expectation of X square part, this part is basically summation of X square by definition into probability X equals to X, right? So which is equals to 0 times the probability X equals to X equals to 0, plus 1 times the probability X equals to 1, right? So because 0 square is 0 and 1 square is 1, right? That's the beauty of this binary settings, right? So again, you are getting P as your value, right? And in the quantum settings, so basically E of X square is simply summation over X square Px, right? P probability of X equals to X, and this is equals to X square mu X, right? Expectation sum over little x equals to binary setting 0 and 1, so which is equals to summation X square mu X. You can take had as an operator, okay? To represent operator, you can take had, and this one. So this is simply as M hat square. Okay? So this is the part. Then our variance in the quantum mechanical setting or quantum computing setting is M hat square minus M hat square, right? Outside expectation outside. Okay. So for example, in this particular case, this is P and this is P square. So this is P into 1 minus P is the variance. So for a single qubit case, this follows the Bernoulli distribution. Okay. Bernoulli distribution. But in a multi-qubit fashion, this can be different, right? How different we'll see. So how it basically what is the let's do a plot quantum projection noise. So we suppose I started with a state rho, okay, instead of sigma, instead of psi. So psi to rho is basically, if it is a pure state, it's a psi and psi, right? And if it is a probabilistic, this psi are probabilistic in nature, right? They have ensembles description. That means the generation of this psi has some noise, right? So then you generate some psi I with probability pi is this set, and you call it as an ensemble. Suppose let's represent this as this one. And then given this ensemble description, we define rho as sum over pi, outer product of psi I, psi I. Okay. Sometimes this digital port creates some noise itself. Okay, so whatever it is, so let's apply, we have a density matrix row, and you apply a measurement operator here, and you get some classical random variable x. Okay, and then let us plot this thing. One is probability p versus this side and this side, right? So variance of the random variable, random classical variable versus the probability to obtain one. So we try to reach towards the probability of one, right, of a particular quantum state. And suppose we start with 0, 0.2, 0.4, 0.6, 0.8, right? So if you plot this, so you will see, so you have our variance is what, like, so our variance is, variance of x is p into 1 minus p, right? If you plot this variance versus this probability thing, right? So var of x, right? Then you will see it's a quadratic equations, right? 1 minus p, so basically this is p minus p square is a quadratic equation. And you will see a plot like this. So this is p minus 1, p into 1 minus p plot, right? And especially if you take the square root of this, then you get the standard deviation of x, which is square root p into 1 minus p. And because probability is between 0 and 1, right? So for that you will see a graph like this, that is standard deviation plot, which is a plot of square root p into 1 minus p. And the values, if you take p less than 1, so of course you can see a more stretched curve for the standard deviation. So this is for standard deviation plot, and this is for the variance plot, variance of x, right? Standard deviation of x, right? So these are the nature of the plot, and sometimes this is called the semicircle plot, and especially when you deal with large matrices, right? There is a, although the relationship is not direct, but in general, when you study the random matrix theory RMT, okay, so you will see this kind of similar kind of plot, and that is called a semicircle PMF or PDF, whatever you say, semicircle distribution, right? Distribution, right, for large numbers. And later you'll see whatever measurement we do, typically the measurement outcome, the value we get, they are the eigenvalues of, this is just a statement I'm writing, but we'll come back in some other courses or sometimes, eigenvalues of the measurement operator or the observable, right? So this is the thing that we can see out of the measurement, right? Especially that's why we often do the G operator measurement, right? G operator measurement. And why we do G operator measurement? The reason is, if you apply a G gate, right? G matrix. What is the G matrix? This is 1, 0, and 0, minus 1, right? So if you apply G to 0, right, you will get 0, right? And if you apply G to 1, right, you get minus 1, right? So what is this equation? This equation is x equals to lambda x, right? X equals to lambda x equation. See, lambda x equation. And in this particular case, lambda equals to 1. And in this particular case, lambda equals to minus 1. So you are applying an operator to a particular computational basis 0, right? And you are getting the same computational basis with the amplitude 1, right? So that means it's eigenvalue equations. And the second part is you are getting the same vector, computational basis vector or standard vector with the value minus 1. You can quickly check just by doing multiplication 1, 0. And 0, 1, right? That is equals to ket1. You just simply multiply this matrix with this vector and this matrix with this vector, and you will quickly see it is ket0 and ket minus ket1, right? So ket0 and minus ket1 means these are following the eigenvalue equations, right? So that's why the computational basis, ket0 and ket1, that is the choice to represent our quantum information, right? Quantum information. This orthonormal basis set is the easiest choice or easiest way to prepare this kind of states, right? Or easier way to represent our quantum state in terms of this 0 and 1, right? And they are the natural eigenbasis for G operator. And you target what eigenvalue you get out of this. Is it +1 or -1, right? And depending on that you calculate your probability, right? So that's why this eigenvalue setting is extremely important. Measurement operator, eigenvalue of the measurement operator is important, right? And later, those who are interested in large matrix analysis and all, you will see the distribution of this for a large matrix. If you have a large matrix A n cross n, right, and that n is very, very large, right, then the average eigenvalue distribution follows this semicircle rule, this particular probability distribution, right? So so this is just a part that I thought might be related, but it has nothing to do with quantum. Now let's move with the other part. Another thing is because our sample space was 0 and 1, right? And x can take any values in 0 and 1, either success or failure, you can say, right? And for this 0 and 1, in order to get the 0, our measurement operator should be this one. Just a summary. And to get 1, our measurement operator should be 1, 1, right? This is a set. So for x, my measurement operator is mu hat x, right? And and in terms of the G operator, you can also write it as in this way. Just for more just a way representation, how to represent in a measurement basis like the Z basis, right? And we calculate this particular quantity, right? So in terms of the probability and this particular part, they are related in this way. If x equals to 0, then probability of x equals to 0, this is just we have calculated, right? And this is also same as in the if you have a noisy quantum state, right? Because all the quantum state you prepare might be noisy due to the preparation, right, of the qubit. So this is also equals to mu hat 0 operator times the density matrix rho, right? So so this is equals to your pi 0, right? So this is also equals to your pi 0 trace of pi 0 times rho, okay? And so this is equals to trace of outer product of 0, 0 times rho, and this is equals to half of 1 plus G operator, okay? So this is important. So because your G operator, what is the eigenvalues of this G operator? +1, -1, right? So if you take the expectation value of G operator with respect to 0, x equals to 0, right? What you get? You get basically 1 plus 0 by 2 equals to half, right? Or if it is equals to -1, then 1 minus 1 equals to 0 by 2 equals to 0 is the probability, right? So similarly for x equals to 1, you can write it as probability of x equals to 1 equals to trace of mu hat 1. Okay, there is a dagger sign. Sorry, I missed this one. Dagger rho. And this is equals to trace of 1, 1 outer product times rho, which is half of 1 minus z. So this part is when you implement it on Qiskit, right? So this is how you prepare the measurement part, right? And you calculate the post probability, right? Um, okay, this part. Okay, so jet part is basically so rho, how you prepare, right? So rho is basically your outer product of psi and psi, right? So you can quickly compute it, like, so this is suppose you take this equals to alpha 0 and beta 1, right? And you also calculate the jet expectation. I'll come, the expectation of jet will check, will come to this part. Okay, how to prove. So this is just a 4 or 5 lines of like lines of thing, and you can just, I'm writing the, this is a different way of writing this probability in terms of the expectation of G. Okay, I'll come this part. Okay. And typically, if it is a single qubit case or singles, in fact, I should say better term is if it is a single short quantum experiment, single short quantum experiment, single measurement sort, right? It follows the Bernoulli distribution. Bernoulli distribution. I'll also share some Qiskit textbook link. So this kind of measurement, how we do in the G basis. So there is a huge details of the calculations. Okay, although I will show in short, but the things are there. Okay, and it follows the Bernoulli distribution, and we all know that for a Bernoulli distribution, if X is Bernoulli distribution with the parameter P, say parameter P, success probability P, success probability P, then expectation of X equals to P, and variance of X equals to P into 1 minus P, right? For a single shot measurement. So it can looks like this if it is the 0th basis, and if this is the 1 basis, right? So this is like 1 minus P, and this is like probability P, right? And if you add this P minus P plus P, that will be equals to 1, right? I mean, depending on how much time you are getting the 0 and 1, it depends on the outcome of X. So this is outcome of X versus the probability of X, this plot. But in general, you can work with many qubits, right? Not just a single particular qubit, but this can be, okay. Can you please mention reference books to learn all this concept explains? Okay, there is, I don't know a single particular textbook where this quantum aspect is discussed. This is just based on our experience from how we do in practical quantum computer. But of course, the probability theory, I shared a book that gives you the A. Populis book, right? All the basics concepts are there. Mm. And quantum information, there are books like the Mark M. Wild book. Yesterday lecture, initially I shared the list of books, but the notes that's I'm writing today, I do not know the direct relation with some books, but the detailed notes that's available on our Qiskit notebook and industrial thing, that I'll be sharing some links. Okay. So for today's class, I think there is less reference, okay, other than these things. But I'll share some online material, online links which are accessible. Okay. Um, yeah. So many things I discuss often based on my studies and experience, but yeah, I do not remember all the resources. Yeah. So now you may have many such quantum state, right? Suppose you have many quantum states and you do multiple measurement, right? Multiple such measurements, and every times you get some random variable x1, x2, and xm. Suppose you do m times quantum measurement, right? M times quantum sorts or quantum measurement. We say it's just sorts, quantum sorts. Okay. So every time you do this, and we get something like x1, x2, x3, and so on up to xm, right? Which belongs to the set this. 0 or 1, right? Every element can take 0 and 1. So this is called M sorts with IID distribution, because each sort does not depend on what was your previous quantum state. Once you measure this particular second qubit, you do not know whether this what is the state of the first qubit, right? That's why they are IID, means they are independent. Each measurement is independent, and but they also follows the 0 or 1 outcome, so they are identical. They are identically distributed. So that means they are IID random variables. Okay, IID random variable. Okay, and the empirical mean for this random variable is basically S is the empirical mean. Empirical mean is basically 1 by number of measurement divided and sum of little m equals to 1 to number of measurement xm, right? For every such basis, you do the repeated measurement, and out of m measurement, how many times you get, you add them up and you will get the empirical mean of the random variable, right? This is very simple, and it follows, expectation follows the linearity property. That means expectation of your a xm plus b xn equals to a expectation of xm plus b expectation of xn, right? For all m comma n and a comma b belongs to some complex number c, right? So so mn can be any real numbers. Okay, they can be some integers also. So this is like for multiple measurement case, and then so there are some, I'll share some more notes on like when you do repeated measurements on various qubits, and initially if there was no error, then possibility for a plus state, right, or plus states is like is something like you get a probability of all of them are equal probability, but due to noise you get slowly that instead of this kind of nature, slowly due to error, so this is coming like this, and slowly you will get Gaussian kind of distribution like this. So once you increase the number of measurement, right? So so the detailed part I'll share, so I'm not covering this part just to save some time. And let me also share a distribution plot. This one can be shared maybe. So just a minute. So let me take this note maybe. Okay, copy paste is not allowed, so no problem. Let me try to directly open. Mm. So I'll share this cheat sheet, those who forgot the statistical detail part. So these all are important. Okay, so the like if it is a like there are some thing like Chebyshев inequality and Chernoff bounding case. Also, so for various cases, what is the condition, initial conditions, and the common form of the PMA probability mass function, so the PDA, and the associated certain remarks on those kind of distributions, right? So this might be helpful. Okay, I'm keeping it in the note. And then let's talk little bit more on the n qubit cases, right? So multi-qubit measurement we'll do now. So I'll give a break after 10 minutes. Okay, so just let me finish this part. Okay, so suppose Now I have a quantum basically algorithm and or a quantum circuit, and that looks like this, right? And so I do the measurement here, 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 and I get some random variable x1, some random variable x2, some random variable x3, and I get some random variable xn. Altogether, if I call this as a capital random variable x, right, where the x is a binary string, this is a binary string, and that binary string basically will contain all these vectors, right? X1, X2. So this way or the reverse way you can write. So X1, X2 to Xn. So this is the like in general mathematical, right, way how you basically represent your binary string capital X, right? But also in Qiskit it is reverse. Okay, so Qiskit takes the last value as first one, right? So Xn, Xn minus 1 to up to X1. This is the Qiskit convention. So if you later find some confusion, so just look back this note convention. So example is basically so it can be 0 0 to all 0, 0 0 to 1, then 1 1 some 0, and then 1 1 2 1, right? So this is the various binary strings that you define as your measurement basis, right? So what do an individual such xi takes the value 0 and 1, right? This xi belongs to this 0 and 1, and finally the state that you call the final binary string that belongs to some sigma, which is basically a n bit binary string, right? This is for I equals to 1 to n, right? So what do I mean? So basically, suppose you start with 3 qubits, 0 0 0, right? And so what is this state? This state becomes your tensor product of these three things, right? 0 tensor product 3. So this is your state here, right? And you implemented some quantum circuit here. Why I am not covering any circuit in this course? So because just after completing this course, we'll start. There is a QT-05 course entirely on quantum computing stuff, right? And we'll detail this part. Today I'm just considering the input side and output side, not in the middle, right? So middle part will come later. So all the quantum algorithm stuff, how to work with this will come in the next course. But in this course, suppose why a particular result we are getting, particular value that we are getting out of quantum computer, how to analyze that result, whether that is correct or wrong, how wrong that is or how correct that is, or how to do the measurement, this kind of stuff, right? So then basically, what are the possible states here? Suppose you get a quantum state phi here, and your initial state you prepared psi, which has multiple 3 initial qubits, right? So tensor product of 3 0, right? So this will be 0 0 0 to up to 1 1 1. So these are the possible state like 0 0 0 0 0 1, so on up to 1 1 1. So there are possible 8 possible states, right? Possible states, and that is basically denoted by this capital X, and individually this thing, right, 0 0 0 that is coming here, here, here. So they are individually xi is the random variable for a particular qubit measurement, right? So now we represent these binary strings x integer, and this is important when you even design some machine learning algorithm, quantum machine learning algorithm and all, how you so everything that you are getting out of a quantum computer is a probability, right? And how you use the probability value to a particular classical feature, right? So we need to understand what this measurement basis tells us, right? So this x has an integer representation, so that is 0 1 up to 2 to the power n minus 1, and this little n is the number of qubit, okay, number of qubits. So this is the integer representation. Also you can expand it to binary numbers, okay. So also we can do in binary representation, binary number representation, that sum of j equals to 1 to n. Just we can write this way, mathematical way, xj 2 to the power j minus 1, right? As in the sum form, right? So writing the same integer form in the as a binary bit string, right? So this is just a convention. These two things are same thing, right? So this is just a bijective numeration, right? So now there were question like about this z. How do I get this z value, right? And I'll come to that part now. So now for 1 qubit, so expectation value of I is P0 plus P1. Okay. So because P0 plus P1, why I say P0 plus P1? Because your identity matrix is what? 1, 1, 0, 0. So if you prepare to measurement operator out of these things, right? So there is one, right? And so this is basically 0, 0 outer product plus 1, 1 outer product. I hope there is no confusion, right? And so this is your this is the thing, this is the operator that will help you to get the probability of 0, and this is the measurement operator that will help you to get the probability of the the qubit is in the state 1, right? So that means this part is helping you to get the probability of 0, and this part is giving helping you to probability the get of 1. So the outcome, if you sum off, you get the expectation value, so P0 plus P1. Similarly, Z operator, if you see, so what is the definition of Z operator or G operator? 1 minus 1, right? So this is basically 0, 0 outer product minus 1, 1 outer product, right? I hope there is no confusion up to this part, right? So this is like P0 minus P1, right? And once you do that, so for this single qubit, these are the two cases. Now for 2 qubits, so we have II, we have IG, we have GI, we have GG. These are 4 different measurement operators, right? So this gives us P00 plus P01, P10 plus P11. Just you need to break the 4 cross 4 identity matrix into 4 probability states, right? And the second one, you will see that IG will be P00, sorry, minus P01 plus P10 minus P11. Third will be P00 plus P01 minus P10 minus P11. And then GG operator, so which is a tensor product of G and G. So you can calculate the tensor product of 1 minus 1, 0, 0. Tensor product of the same thing, 1, 0, 0, 0 minus 1. Whatever you get, and break that into 4 measurement basis, right? So you'll get P00 minus P01 minus P10 minus P11. So these are the like the expectation of various measurement operators that we do, right? So now if I stack them, right? Now if I stack this left hand side, this part, right, and I define G as a vector, right? That vector is, if you can denote like this, so I G GI and GG, right? And the probability values, so basically then you can define a W as 1, 1, 1, 1, 1 minus 1, 1 minus 1, and 1, 1 minus 1 minus 1, and 1 minus 1 minus 1, 1. So we have seen this matrix, right? This matrix we know, right? In the first class, linear algebra last week, we have seen this as this is same as the Hadamard matrix, Hadamard matrix, Hadamard matrix minus Hadamard matrix, right? 2 plus 2 Hadamard matrix, 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 right? So this is coming from this picture, right? And suppose let us define P as one vector with the element P vector, probability vector with the element P00, P01, P10, and P11, right? So then this entire equation that we can write as G vector equals to W matrix into P vector, right? And from there you can calculate the probability vector is equals to 1 by 2 to the power n for nth qubit, right? So W into Z, right? So this is what? This is a Fourier transform, right? Fourier transform, and the special case that we are using here is basically Wahl-Hadamard transform, right? Wahl-Hadamard transform. So the measurement basis representation, the entire possible spectrum of the measurement basis, right, is just the Wahl-Hadamard transform of the probability vectors, right? Probability vectors, and hence the probability vector that you get is basically inverse Fourier transform of, right? So inverse Fourier transform of the G, right? So you can write as a dagger here for simplicity, right? So that's how we can also compute the probability in this way, right? And this is a like a compact way of representing for 2 qubit state representation, or the 2 qubit measurement operator representation, better to say, and the possible probabilities, right? You take time. I understand that this part is not like one day you will get understand, because many from many materials I prepared these things. So and much earlier also I need to recall what are those materials. But yeah, I mean, slowly when you just run the Qiskit code slowly, I'll demonstrate one code today. You will recall that these particular relationship, especially when you solve linear system of linear equations, for example, HHL algorithm, right? We'll see in the QT-05, we'll see the first part of the algorithm, for example, the HHL algorithm. The detail we'll see later. Suppose you have a set of linear equation you want to solve, right? X equals to B equation, right? So you need to find the X hat, that is A inverse B. But the existence of A inverse is a question, right? So you can always go for A dagger B, where A is the pseudo inverse, right? So basically you prepare B as a ket B operator, right? And that operator you represent as a sum beta I over I into the eigenbasis vector of A, like eigenbasis if they are, say, EI, where EI are the eigenbasis or eigenvectors of A, right? If somehow you can represent this way and you prepare a quantum circuit here, so you start with many such ket 0, then you do something such that you prepare the state ket B, right? And then you'll see that you are applying a quantum phase estimation algorithm here. And whatever you have done, ultimately at the output, you are doing a inverse quantum Fourier transform IQFT here before considering the result here. So you are computing 1 by lambda and all, and then finally you are getting certain solution, which is a function of the solution fx hat. So we'll see how this algorithm work, but the fundamental is why we do this kind of inversion process before the measurement. And one of the thing is this one. Okay. So this is just the way how we do it. Okay. One thing is that coherent noise, the measurement or the projection noise we have seen. And I'm taking a break of 5 minutes and we'll come back. We'll close the Okay, so let me close the measurement noise part and then directly we can give a 10 minutes break and we'll come back with the teleportation thing, right? So now we'll go to the measurement noise part. So suppose now in this particular case, suppose we have a quantum information psi and we are expecting x, right? The random variable x. But suppose in the measurement instrument there is some problem. And what we are getting is some y, which is noisy, right? So the error is coming here, right? So error, where the error may come, the generation of psi, there may be error. It is passing through some quantum algorithm that you may have some error, that you may interact with the environment, there is some error. In x, that is a random variable due to projection, that random variable is coming, that may be uncertain. That x might, when you actually measure with some instrument, there is some additional error, right? And also this qubit, when you place on a hardware, right, qubit 1, qubit 2, they may have like coupling error. So there are lots of errors in quantum computation hardware, right? And I'll name those errors, and some of the errors, I mean, most of the errors as a categorical way we have studied, right? But you can always go for example, if you are interested for in the coupling error, right? So how, if you place two qubit close to each other, how much interference the second qubit does in the information of qubit 1, right? So these are like much deeper topics in quantum measurement. I'm not going through. So now suppose now this part is, see, this x is classical, this y is classical. So this part is pretty much we know, right? How we know? Suppose this is very same as the classical information theory. So ideally we have the random variable or the bit x should have value 0 and 1 I should get. But because of the measurement instrument error or the measurement error, so this 0 can become 1, right? Sorry. This pen is making a lot of error. Yeah. This 0 can give 0, 1 can give 1, or this 0 can make error and give 1, and 1 can make error and give 0. So suppose the probability that 0 gives the output once with error epsilon, right? And suppose 0 gives 0 with the success probability of 1 minus epsilon. Similarly, 1 gives 0 with probability v is the error probability, and 1 minus v is the success probability of 1 gives 1, right? So this is for the noisy bit y, right? Now, if this epsilon and v, they are same, right? If they are same, then we call it a binary symmetric channel, right? In classical communication, symmetric channel, but it can be very different in quantum, right? So because this epsilon and v may be very different. So so p ideal can be written as the probability of x equals to 0 and probability of x equals to 1, this part, right? And this middle part you can write as a matrix A, right? Which is something like this: x equals to 0, x equals to 1, y equals to 0, y equals to 1. 0, 0 has the probability 1 minus epsilon, and this 0, 1 has the probability epsilon, and this 0, 1 is this nu, and 1 minus nu, right? These are the case. And I can always define another vector p noisy, noisy probability vector as p of y equals to 0, p of y equals to 1, right? So hence I can always write the actual measurement that I am getting output, noisy output, that is equals to the matrix A times the ideal, p ideal vector, right? And this is the matrix or the channel matrix or the error channel matrix that is coming due to the measurement noise, right? Measurement noise. So now there is a quantity, an important quantity that we need to consider, that if it is an ideal measurement, right? Ideal measurement means whatever the expected result that I am getting without any error, that means A is an identity matrix. Identity matrix I. If it is not an ideal case, then this A matrix has the element just we have seen, right? A equals to your this 1 minus epsilon nu and 1 minus nu, right? Which is of course a non-diagonal matrix, right? So one of the methods, that classical approach, what we do, we try to improvise this diagonal part with some regularization constant, right? A plus lambda A. In classical regression methods or ridge regression, Tikhonov regularization, this kind of methods, we try to put more weightage in the diagonal part, right? And we try to reduce the off diagonal part, and that's how it improves the rank of the matrix, the condition number of the matrix and all. So that is the approach, that how we improve the health of the matrix. So this is health of the matrix. To improve, you need to basically put more weightage towards the diagonal. So that matrix you add with a lambda I part here and you reduce it. So that is like a post-processing techniques, how you reduce noise and all. And there is a huge study on that. Those who are interested, they can study this topic called tomography, right? So quantum tomography, classical tomography, various approach. So whatever result you are getting, how to improvise the result. And you see there are approach like classical methods, like how you improve the health of a matrix, in fact, right? So mathematically, you are improving the health of the this particular matrix such that your noisy result is closer to ideal result, right? So there, these are various post-processing techniques. Post-processing techniques, and there are lots of research papers, and it's one of the active research areas, how you use a quantum circuit result as a, say for example, a machine learning applications, right? So suppose there is a quantum circuit, the state is psi, right? And whatever you are getting, so out of the so you design some algorithm here, right? And you get some phi state here and you do a measurement here. So you are getting some x1 to up to xn number of output, right? And you need to reconstruct this state. Suppose, for example, for a particular application, so whether you want an image classification, you want to reconstruct a signal, right? Suppose a signal is transmitted from antenna 1 and received here, right? How you can reconstruct this particular X signal that you are seeing in the Y, right? So various reconstruction problem in quantum communication channel. So people, whatever output they get, so they represent in this way and they try to minimize the measurement error in this way, right? So this is like, you can improve in other ways also, but this is just typically a problem. Okay. And then now if you calculate the probability of y equals to say 1, probability of y equals to 1. Mm. How to calculate this? Probability of y equals to 1 or probability of y equals to 0, right? So this is like probability of y equals to 1 given x equals to 0 into, this is a conditional probability, just probability of x equals to 0 plus probability of y equals to 1 into given x equals to 1 into probability of x equals to 1, right? So this is equals to epsilon 1 minus px plus 1 minus nu px. So this is equals to epsilon into epsilon plus px. Px is the probability of x. 1 minus epsilon minus p. So this is the probability of y equals to 1. So there is one important thing. Some of the topics, let me. So basically, as you improve the number of observations, right? So our result gets more and more improved, and so there are more noisy cases, right? Especially the depolarization channel, and other various kind of channels and all. So I haven't given the description of row, and I haven't talked much about this U, right? Suppose U is like U has an interaction with the environment, right? And suppose this U has a system U and environmental U, right? E and V, right? And then there is a composite quantum system like U system versus the composite U, E and V, right? And then this composite system, given this composite system, and we receive some informations here and we do the measurement, right? So how to retrieve maximum information about the row from this measurement result? So there is a lot of things like quantum channel and all. So we'll come back to this part in QT-06. Okay. So with this, I'm closing the first part of the session, and please take a break of 5-10 minutes, and we'll come back with the quantum teleportation principle, and we'll see some Qiskit demonstration for that. If you have any question, please feel free to put in the chat box.
Mustafa sir?
Yes, sir. Shall we start?
Yeah, we can start. Yeah, I was just thinking whether you are waiting for me. Right.
Yeah. Thank you.
Yeah, thank you. Okay, sir.
Okay, so now we'll start a new topic, quantum teleportation. I think I haven't covered this in other courses also. Okay, so certain things I skipped, but I'll share this note of Dr. Slatko in our IBM Quantum. So the things that I was covering and some extension of this, um, some extension of this to various other noise cases, right? Although I'll come back and I'll take much detailed on the noisy quantum noisy channel, especially this thing and this trajectory concept, quantum trajectory. So these are some other quantum noise models, right? And bit flip channel, the phase flip channel that yesterday we discussed a bit about the role of the poly X gate, poly Z gate, and their implications. Also, when you have a basically some sort of the polarization, like the amplitude damping cases, right? So your representations of the blosphere is no longer have the unit norm, right? So it's like squeezing of the quantum state blosphere, squeezing of the state representation of a particular state, which is not an ideal state now due to the noise part and shown here. And also some more concept. So suppose you interfere in the unitary matrix that I was talking, it interacts with the environment, and then how much quantum information you can lose. So we'll come back to this kind of concept with something called the Krauss operator, right? Krauss operator representation for various quantum channels. And I think this is already Dr. Ritojit covered, like how to mitigate the errors for the coherent, incoherent case. So some of the noise model he had shown, and you already have done the programming for that, right? So now today we'll cover the quantum teleportation part. So I thought let's do at least one algorithm in this course. And it's not an algorithm, it's just a like approach how we do it. So there are three points. One is the quantum teleportation. Then there is more two topics I'll take later. One is the super dense coding, and one more topic is the CH/SH game. Right. This all together completes the quantum information, at least PG level, right? So these two topics are future topics. If you are interested, you can have a look, but we'll cover this particular topic. So we to study this quantum teleportation, right? So we need to introduce two basically names. One is Alice and one is Bob. These two names are common in cryptography, security, and everywhere, right? Alice and Bob. So these are just names given to some hypothetical entities. And or agents in systems. And systems or protocols are games that involves exchange of informations, and they are assumed to be in different locations, right? Different locations. So and then two more thing we have to know. This is like these are the two entities, and then another two part is the entangled state versus the probabilistic state. Okay, entangled state versus the probabilistic state. So a simple an entangled state of two qubits is written as this often also known as the Bell state, right? And one of the four Bell state is 1 by square root 2. For two qubits, it's 0, 0 plus 1 by square root 2, 1, 1. Okay. And similarly, two bits probabilistic state states of two bits, not qubits, bits. Okay. Each is written as half of 0, 0 plus half of 1, 1. Note that they are not at all same. They are very different. In quantum information and computation, we view this entangled state as a resource, and that can be used to accomplish different tasks. So they are not at all same. I have some lectures in the MNIT courses. I'll share the link. There you will see why this is an basically distinct state, right? And why can't I basically decompose this into the single qubit state? Probabilistic state you can always decompose into state of 0 and 1, but this particular state you can never represent in the individual single qubit case. So this is a very distinct property, and that is only observed in the some of the quantum materials or some of the quantum phenomena. So where a particular qubit, suppose this is a qubit 1 or quantum system 1, and they have another quantum system 2, and they have some natural correlation, quantum correlation. Right, so this is a very deeper. There is deeper concept of entanglement. In fact, the discovery around 1940s by Schrodinger, the main source of the discovery or main reason or main the idea or the motivation for discovering entanglement was on various thought experiments, and one of the thought experiments was EPR paradox, right? Einstein, Podolsky, and Rosenberg. These thought experiment, right? Um, on the correlation, quantum correlations of quantum phenomena, right? And once two particular qubit they are in entanglement, right? You cannot represent this two particular qubit individually. Mathematically, you represent 1 by square root 2, 0, 0, and 1 by square root 2, 1, 1 state, right? So I have a proof of this also, why you cannot do this. So I'm not repeating that part here. Now, two additional terminology also we need to know. So I'll come back to this picture. Whether I can increase the size of this picture or not, I don't know. Um, okay, leave it. Okay, so two terminologies. Terminology. One is that we say we view. So because these two particular qubit, when they are in the entangled state, right? So we view the state I plus as representing one unit of entanglement. So together as a single unit of entanglement, that we call an E-bit. Sometimes people call this probabilistic bit as a P-bit, this particular thing, but E-bit is very different from the P-bit. Okay, so we'll only stick to E-bit part. Okay, and we need to know certain basically terminology. One is Alice and Bob share an E-bit, that they are far away, but they have a correlation that is shared by one entangled bit, that is E bit, means Alice has a qubit A, Bob has a qubit B, and together the pair A comma B is in the state 5 plus. So this is the first terminology that we need to consider. Okay. Now let us look to this particular picture. Okay. Suppose this is the qubit that is corresponding to the qubit for Alice, and this is the qubit for Bob. Okay. And they have a shared entangled E bit as 5 plus, right? And the scenario is something like this. So there is the scenario. Oh, sorry, why this color? Scenario is that Alice has a qubit. Alice has a qubit Q that she wish to transmit or transfer, you can say, to Bob. Transfer to Bob. Better to say transfer to Bob. So Alice had some information, quantum information that's stored in the qubit Q or represented by the qubit Q, and she wished to transfer these informations to Bob, right? That's the main objective here, right? Now, the situation is as such that although Alice has this qubit Q that C wants to transmit to B, but C cannot. Alice is unable to physically transfer because this generation of the Q, that quantum system, right? Whether it's a photonic or it's a cryogenic setup, right, or some setup, right? So physically, you cannot send this Q. Unable to send physically this Q to Bob, so C is only able to send the classical information out of this Q to Bob. So if Q suppose Kate psi, okay, let's me take suppose Kate psi mm, equals to alpha Kate 0 plus beta Kate 1, right? Now this is a quantum information, right? Because the probabilistic values are alpha and beta, right? And only C can transmit either alpha or beta classical information, not with the superposition state or the entire thing, right? So she has to measure it and then transfer the classical informations to Bob. That is one condition. And then Alice and Bob also share this entangled state 5 plus, right? But somehow you have to transfer this the qubit Q, which has the quantum state psi. That psi state should appear to Bob. Okay. And for that, we'll design a quantum circuit. Okay. So how to do that? Let's come to the picture. So the scenario is something like this. The scenario is suppose the classical information out of this psi state, right? I'll do something, and after that I'll do measurement, and after the measurement I will have classical information B and A, right? And that B and A, I'll design a classical communication channel and I'll send B and A to Bob. And based on the values of B and A, Bob will take a decision of what the quantum state should be, right? So that's the phenomena of quantum teleportation. And now let's establish the relation. So now first we have to note certain things before we do this thing. First of all, the state. I will implement this algorithm in Qiskit today, so no need to take much pressure. So the state of Q is unknown first of all because it's in quantum state, right? And it is unknown to both Alice and Bob because it's not classical information. So Alice also cannot see what is Q. Okay. Second is the correlation including the entanglement, right? Correlation in including the entanglement between Q and other system. Other system must be preserved. Must be preserved by the transmission. So what does this sentence mean? Means, so suppose this Q had some entanglement with some other quantum system, right? So suppose this Q had some basically relation with some other quantum system, right? Some entanglement or something. And that relation should also, when we transfer the quantum information from Alice to Bob, that should also hold. That should not be cancelled or that should not vanish. Okay. That is another condition. Third is the no cloning theorem. I have the rigorous proof of the no cloning theorem in one lecture. I'll share the link. The no cloning theorem no cloning theorem implies that if Bob receives the transmission, the information or the transmission, Alice must no longer have the qubit in its original states. Original state. So what does it mean? Once this information is transferred from Alice to Bob, and once Bob gets that information, then Alice should not have the original information here. That means mathematically this can be written as the no cloning theorem, NCT no cloning theorem states that there is no quantum algorithm. There is no such quantum algorithm exist or quantum operator exist such that you apply it to some empty register and try to copy the information from another register to that empty register, right? Such that you prepare this psi state, right? This is never possible. That you copy that information and that same information will remain in the other register, right? So that is never possible. So that means there is no universal copier machine exists in a quantum computing setting, given that this is not in the 0th state, right? So this is the principle of no cloning theorem, that you cannot copy quantum informations, right, and transfer it to another quantum register. Once you transfer, then that particular quantum information will be interrupted, right? It won't be in the original state. So that is the settings. And initial condition, what I considered that they share an E bit. That means AB pair is in the state. Initial condition, let me write again. That the pair AB, they share an E bit, that is the 5 plus state, right? And Alice has also additional qubit, also this Q register, that is the qubit, right? Q qubit that C is to transport to Bob, right? This is the initial condition, right? Now we'll design this thing, and there is a protocol how we do this, right? The protocol is very simple. So first what it does, okay, let me take a different color for this thing and remove this part. It's not erasing. Okay, fine. Okay, so first, what does Alice performs a control C operations between the quantum information register, that is the Q registers, and the registers A itself, right? So first, it does a C naught operations, right? Conditional not operations, where Q is the this particular register, quantum register, is the control qubit, and A register is the target register, target qubit. So in this way, you apply the C0 gate, and then you apply a Hadamard operation on top of the this particular case. So on the first qubit Q, right? So Alice, after doing this, it does the quantum measurement. So if it does the quantum measurement, right, obtaining the binary classical outcome, say the outcome is B in the control register, and the outcome is A in the target register, right? And this information, classical information, it reaches to B Bob B register, right? Bob. Then Bob performs two particular operations. So what Bob does is Bob take decision this way. Bob take decision if A equals to 1, then Bob applies X Pauli X operation on qubit B, and if B equals to 1, classical information B equals to, because classical information A and B can take value of 0 and 1. If B equals to 1, then Bob applies G operation, Pauli Z operation, Pauli G operation on qubit B. Now, because there are two qubits, right? So for Alice, so one is the Q qubit and one is A qubit. So what are the possible state? 0, 0, 0, 1, 1, 0, and 1, 1, right? So accordingly, Bob will take decision, so that if it is 0, 0, then if it is 0, 0, then Bob will do nothing, right? So it will apply identity operator, means nothing on qubit B, right? Qubit basically register B register. Now if it is 0, 1, so that means B register B equals to 1, then it applies G operator on the qubit state B. If it is 1, 0, it applies X operator, and if it is 1, 1, then it applies both X and G operator. That means G will come first and then X. So right to left, X and G operator, right? So these are the operation it does based on the conditioning of A and B, which are the classical information. But the decision is taken on the quantum registers. Now, what are the implication? It happens just by taking this decision. Let's see the implications. So immediately, what it does is that this is the circuit now. So suppose the outcome here is the pi 0 state, then pi 1 state after the C naught, after the Hadamard it is pi 2 state, and so on, right? So what is your pi 0 state? You applied the Hadamard gate, right? So initially all are 0, right? So once you apply the Hadamard gate, right? So in Qiskit, the formulation is like it will just let me take a color. Mm. So this is your first qubit, right? This is your second qubit, and this is your third qubit, for example, right? So if you go from basically bottom to top, then you see so once you apply the C naught gate, right? So before the C naught gate, what are your possible state, right? So this is your pi 0 state before anything. So this is your pi 0 state. So pi 0 state, how you prepare? Because you initially your this registers size state in the register Q. There are three registers Q, A, and B, right? So Q registers has the value alpha 0 plus beta 1, right? And you need to do tensor product with this second A register and B register, right? So what are the possible state? Possible state is this 0, 0, 0. So A 0, 0, alpha 0, 0, then alpha 1, 1, 0, and beta 0, 0, 1, and beta 1, 1, 1, right? So these are the this is the possible pi 0 state here. So this is just a tensor product of this, and this, right? Now, once you apply the CNOT gate, then what are the outcomes we can get, right? So yes, like last week I said, the application of CNOT gate, right? The CNOT gate is like this particular operator, the outer product of 0, 0 times identity plus outer product of 1, 1 times x, right? So that means once it finds a 1 in the as an initial qubit, it flips the second qubit, flips the second qubit, right? So if I look at in this particular picture, so this is 0, no problem, this is 0, no problem, but this is 1, then this particular qubit has to be flipped, so this 0 will become 1, and this is also 1. Once it is 1, then this particular qubit has to be flipped, so it becomes 0. So you need to count from right to left. So this is your first qubit, second qubit, third qubit, first, second, third, first, second, third, first, second, third. So wherever you find the first qubit as 1, then second qubit will flip. So this is the state after your CNOT, right? Now you apply Hadamard. Where you have applied the Hadamard? You applied Hadamard in the first qubit. I mean, in the circuit, it's in the third qubit, right? So once you apply in the Hadamard in the third qubit, only this 0 will become plus state and this 1 will become minus state, right? For by applying the Hadamard, right? So this in this case particularly, this will be alpha 0, 0 plus state, then alpha 1, 1 plus state. This 0 will become plus state, right? And then beta 0, 0, 1, 1 will become 0, 1, and 1. So basically, I should say, how I should say, 1 will become minus state, right? This 0, 1 and minus state, and this 1 will also become minus state, right? And this 0 becomes plus state. This become plus state. So altogether alpha 0, 0 plus state, alpha 1, 1 plus state, beta 0, 1 minus state, and beta 1, 0 minus state by square root 2. Okay, so this is the conceptually the thing is not that difficult, but you have to be very slow in this stage, and you need to do by hand calculation till this state, right? That you are getting this state or not. Now, once we get that, we have to be very serious in this particular SPI2 state, right? So now let's just 1 minute. So if we look at in the pi2 state, right, then you can always break this plus state as 0 plus 1 by square root 2, right? And minus state as 0 minus 1 by square root 2. Because this is just you are getting by applying the Hadamard, right? So you are getting plus state, and 1 you are getting by applying Hadamard, you are getting minus state, right? So then our equation becomes this one just by then another square root will come here. So square root 2 and square root 2 will become 2, right? Because this plus state also contains another square root 2, right? So square root 2 will be 2. And you just break the equations like this. Then you just put this just a tensor product from this Eigen tensor product like 0, 0, 0 and 0, 0, 1 and so on, right? And once you do that, you can then basically combine in terms of this particular state alpha 0 plus beta 1, alpha 0 minus beta 1, alpha 1 plus beta 0, alpha 1 minus beta 0, and the two basis things. So why I am shifting from this side to this side? Because in the circuit, this part is fine. This is the transmitter part. This is done. Now we are coming to this AB register part, if we can represent the information in this two way, because they are in the EBIT representation form, right? Then we are done, right? So we are representing the information earlier with the most of the thrust was this side. Now the thrust is towards this side, right? Now once you do that, and you can do the basically measurement, right? Once you do the measurement, you get the probability as the square of this, right? Square of half is 1/4, and this internal part will become 1, right? So all the internal part will become 1. So the probability of all the possibilities like 0, 0, 0, 1, 1, 0, 1, 1 all become 1/4, right? So immediately what happens? So let us do certain things. So pi2 state, as half of alpha ket 0 plus beta ket 1 0 0 plus half of alpha 0 minus beta 1 0 1 plus half of alpha 1 plus beta 0 1 0 plus half of alpha 1 minus beta 0 1 1, right? This is my state. Now if I have the classical state AB, which has the possibilities 0 0 0 1 1 0 and 1 1, right? And my probability that I just saw, probability is 1/4 for all of them, right? There is no issue. Now conditional state. Conditional state. What are the conditional state? B from bottom to top, B, then A, then quantum register Q, right? So what are the conditional state here? The conditional state are alpha ket 0 plus beta ket 1 0 0. Second case is alpha 0 beta 1 0 1. Third is alpha 1 plus beta 0 1 0. And fourth one is alpha 1 minus beta 0 1 1, right? Now operation. Let's do operations on operation from the Bob side, right? Operation on B. Bob side on the register B, quantum register B. So what we said, if the probability is just alpha 0 plus beta 1, right? So basically alpha and beta means the P0 and P1, right? Then we will do nothing, means identity operations, right? So if I do identity operation, then I'll get alpha 0 and beta 1, right? Now if I do on this particular state, so there is a I wrote it wrong way. This is minus, right? So minus. So if there is a minus in the information, like if the B qubit is 1, sorry, B classical bit is 1, then if the classical bit is 1, then I will apply a Z operator here, right? So if I apply the Z operator, then this minus will become plus, right? So it will be alpha 0 plus beta 1. Now the third part is the first information is 1. First classical information is 1, right? If the first classical information is 1, then I need to apply a X gate, right? If I apply a X gate, what I'll get? I'll get alpha. It was alpha ket 1. It will become alpha ket 0, and beta. There will be bit flip. Beta will be by applying the Z, I have done phase flip here, and I'm doing bit flip here, right? So in this particular case, and once the classical information A, B both are 1 1, right? then both are 1 1 means I have to do both the phase flip and the bit flip, right? If I do phase flip, then this minus will become plus, right? And this 1 will become 0 and 0 will become 1, right? Alpha 0 plus beta 1. In all the four cases, you see the final state. That final state that we get, that is all are only psi state. That means you have transferred the information successfully from here to here. So this is the information that was initially it was here, and it is you are getting here. So you actually physically haven't transferred anything from your transmitter to receiver. They can be very far apart. Only the concern is that the Alice and Bob has to be sharing a one unit of entanglement, right? If there is a one unit of entanglement between A and B, you can transfer the information from basically transfer the information from Alice to Bob without any physical transfer of information. That means you transfer the classical information, and based on the classical information, Bob basically performs some bit flip or phase flip, right? By doing the bit flip and phase flip, it reconstruct the original state psi, right? And that we have proven here, right? Now you can say that my circuit can have instead of psi state, that was earlier alpha ket 0 plus beta ket 1, now it is doing entanglement with a bigger circuit, right? And means there is a huge information this side, right? And now you represent the psi state as this way, right? So can I transfer this information from here to here? Of course, you can transfer the information. So you can similarly prepare this particular state, and you calculate the phi with the same circuit, the pi 0, pi 1, and pi 2, and then you check the probability, and then you apply these I, G, X, and Gx. Okay, so you'll see that ultimately you reconstruct the psi state, right? Okay. So with this, let me write some notes. So one is, uh, first of all, teleportation is not an application of quantum information. So it performs quantum communication. Quantum communication, it helps in quantum communication protocol. Secondly, teleportation motivates a concept that is called the entanglement distillation. I'm not covering this part. This is a very advanced topic. It is used in um, many quantum information theoretic research for reliable communication. And also beyond its potential for communication, teleportation has fundamental importance for the study of quantum information and computing, right? So with this, I close the theoretical part, and just allow me 2-3 minutes to set up the Qiskit, and you take your laptop and all. So we'll start the Qiskit session in 2-3 minutes. Okay. If you have any question, please feel free to write it. I can see one question maybe, but the received psi as measurement will destroy the initial state. Of course, of course. Do we have the real world example of teleportation? um, Real world example. So basically, I don't know. I mean, of course, people are using quantum communication in the QKD and various security aspects, but how they prepare the information on a photonic setup, I do not work in that particular thing, quantum photonic setup. So, of course, I mean, this is possible, right? But the hardware equipment and the people, so those who work in the communication setup, they are the better people to answer these questions, right? Yeah. But of course, like in the security and all, we use a lot of quantum communication protocol. Teleportation is just like phenomena, right? And it has lots of use cases, especially if you use the entanglement distillation, for example, right? So it has many use cases. So I mean, I haven't done any research work in that area, particular area, so I can't say much, but it has use cases, yeah, in general.
Sir, Dr. Mustafizur?
Yes, sir. Am I audible?
Yeah, now what?
Yeah, I just stopped the whiteboard part. So I'll
Oh,
share
okay,
now
okay.
the
Right.
VS Code. Yeah, I mean the Jupyter thing.
Okay, okay. Yeah.
And is my screen visible?
Ah, yes, sir.
Okay.
Maybe you can make it the white screen, but that's okay.
I,
That's okay. Make
yeah,
it, increase the size.
yeah, I'll increase it. Setup always takes some time.
Ah, no problem, sir. Take your time.
Is visible now?
Yes, yes. Now it's better.
Right. So I just gave 2-3 minutes for the audience also for them to set up
Yeah. They
so
can
that
take
they
their
can
time. Yeah.
directly code with me.
Participants, keep your things ready. Yeah, 1 or 2 minutes we'll wait.
Mhm. So I hope that you have implemented. I hope you have installed the Qiskit because there were I think already you have done some programming stuff, right?
Yeah. That part is done, sir. Yes.
Yeah. So first check the the Qiskit version. So you can import the Qiskit package and import versions, and let's check the versions of this. For me, it is 2.2.1. If you want to install the, if you have the previous version, you can just simply do the pip install Qiskit, this command, and it will install the Qiskit software. If you have specific requirements, say suppose you want to use the 1.0 version, so just you need to do Qiskit equals to 1.0 and it will do the installation for the 1.0 versions, right? Now, so we need to import certain packages for this code, this quantum teleportation implementation. So from Qiskit, import certain tools. Is for example, the quantum circuit, then quantum register, then classical register, right? Because we need to also transfer the classical information to Bob, right? Classical register. And to do the experiment on the simulator, we'll be using air simulator. So from Qiskit air, we'll import air simulator, right? And for visualization of the probability and certain things, we'll use the visualization tool. For that, we have Qiskit dot visualization spelling error visualization Qiskit dot visualization import plot histogram, and then we'll print the matrix. So sometimes printing matrix directly from NumPy is not that great to visualize. So we'll take array to latex to see latex part. We'll take we'll to find the result. There is a package Qiskit result. From Qiskit result, we import something called marginal distribution. This might not be required, but you can take it for good visualization. And then there are chat questions also. So let me do the setup here. Is it, sir, is it Jupyter? Can you please shift back? And no, I am using VS Code, okay, not Jupyter. So because for industrial use cases, this is preferred, okay. VS Code is another environment. So this is like any programming I can do in VS Code. It requires a pretty much bit more RAM and all. if you have a good computer, you can install a VS Code. It can write Python, C, Rust, various programming languages in the same place. Okay. Um, okay, but you can easily do it on the Jupyter just by installing Qiskit and certain tools, right? Yeah, and then we need to import the library from qiskit dot circuit dot library import u gate, for example. So this is a unitary gate directly I'm calling, right? And then, okay, what are these things? And then from numpy, I am importing the pi and random. So these are some particular libraries I'm calling for the program. Is it VS Code? Can you go from starting cell onwards, because the black screen we can't able to see. Yeah, this I just started like from here. There is nothing in the above. Let me check if I can change the color of the display. I'm not sure. Hmm. VS Code, I think it's in black screen, right? Is it possible to change the screen color for VS Code? I'm not sure. Um, VS Code setting. Okay. Um, is it not visible this screen? Like I maximize the size, right? I mean, if you face some problem, maybe you can just rejoin and increase your brightness of your display, maybe. Right. It's sometimes good for us, saves our eyes. Yeah. Mm. Okay, let me also give you this thing in the chat box also. You can directly copy from the chat box, right? Now let us define certain registers in this settings. Suppose we take a qubit and as a quantum register 1, 1 comma, and we rename this as q. The first qubit is q, right? And we take a bit 0, and suppose that bit 0 is quantum register as 1. We take one quantum register for one bit and name it as a. We take another bit 1 for Bob equals to quantum register 1 comma b. These are just naming, okay? So you don't need to panic. You can take other names also. Just and then we take a equals to some classical register, right? You take a classical register for the classical information little, and you can take a classical register for b. classical information B, right? So now we prepare a protocol and we call that protocol as quantum circuit, and then in this particular protocol we have a qubit, we have a e bit 0 for Alice, we have a e bit 1 for Bob, and we have the classical register A and B, right? So this is the setup part, and let me share the code here maybe, right? Now for the teleportation part, let me reduce this terminal part. Now, so now we'll prepare the EVIT used for teleportations, right? Let's prepare the EVIT for the quantum teleportation. So for this, what we are doing, because we name our quantum circuit as protocol, right? So in the protocol, if you see in the note what we have done, protocol.h, in the first qubit we will apply a Hadamard, right? So in the e bit 0, and then we also do protocol dot cx. There is a control x operations, right? On the e bit 0 and e bit 1, right? So we apply a Hadamard. So how we create the Bell state? We apply a Hadamard and then we apply a CX gate, right? Hadamard and CX. Yesterday we have seen this, right? You apply first Hadamard, means you create a superposition state, then you apply a CX control NOT gate, CX gate, between Alice and Bob, e bit 1 and e bit 0, right? E bit 1 and e bit 0. So this is how you prepare the entangled state. Okay, I need to increase the size. Is this fine? Protocol.h e bit 0 and protocol.cx e bit 0 and e bit 1 means you create a Bell state basically, right? Or the entangled state. So e bit 0 and e bit 1. Now once you do that, then I just I just do protocol.barrier. So this is nothing. This is just for the good view. Then protocol.draw. So this is like this. What I have done, I have a Q register. I have a register A for Alice. I have a register B for Bob, and then I apply Hadamard to Alice and I apply CX between Alice and Bob for this entirely prepare the one unit of entangled information, right? There is a barrier mean just to visualize the circuit in a better way. Okay, I can do MPL also most likely. Yeah, so now this looks like this, right? Oh, so I need to clear the circuit. So just 1 minute. So because I run the circuit twice, so it creates two code of information. So for that, I need to erase that circuit protocol dot clear. I need to do. Okay. If you clear, the circuit will be clear, and then again, if you run, you'll see this information. Okay. So anytime when you see something is repeated, you can do circuit dot clear. It will clear the circuit. Then again, I apply the prepare these things, teleportation thing, Q, A, B, and A, right? So let me share the code for this part. And if you are running the things twice, and if you see something is problem, you can do protocol dot clear, and you can rerun the circuit. Okay. Now, what I have to do is You can see the classical registers are represented by two line wires, okay, and quantum registers are represented by single line wires in Qiskit, okay. Now this is just a convention, okay. Now we have to do the Alice operation first, and then we'll do Bob's operations, right? So we'll first do Alice operation. So if you see the circuit, right? Let me check if I have the circuit. Just allow me 1 second. So if we see the circuit here, you can see the circuit, what it is doing. First I created this EBIT, right? Now I have to do this operation, right, on the Q resistors, between the Q resistors and resistors of C naught and Hadamat. Then I'll do the measurement and I'll retrieve B and A. Then I'll transfer these informations to B, and then B will do these X and G operations, right? So that I have to follow, right? So then what is the Alice operation? So protocol.cx protocol.cx between the registers, there are two registers. A qubit is the first register, and the second one is the ebit 0. Ebit 0 means Alice, okay, name of the register for Alice. Now it will do a cx operations, then it will do a Hadamard operations, right? Protocol.h. So protocol.h in the first qubit, right? The qubit q. Then I can do a barrier, right? Protocol.barrier, protocol.barrier, and protocol.barrier, and I can draw this protocol.draw. See, so okay, MPL I can do. Okay, that's okay. I mean, first what I have done, I have created a EBIT between A and B, right? And then what I have done, this part of the circuit, like between the quantum register Q and A, I created an entanglement using the C naught, and then I applied a Hadamard, right? The second part of the circuit is done. So this is the operations done by Alice, right? Any confusion so far till now? If you have any problem, please let me. I mean, I can wait for you. So if you put MPL, it will give you color circuit. Okay. So let me. So our circuit looks like this. Right? Now once you do that, then now the next purpose will be doing the measurement, right? So the next job is Alice performs measurement and sends classical information to Bob, right? So to do that, what I have to do, Alice measures means protocol dot measure, sir, there is no need to create any Qiskit environment setup because we need to do it in Jupyter. And there is no need to create any Qiskit environment setup because we need to do it in Jupyter. No. Those who are using Jupyter and all, you need to install Qiskit visualization 2-3 toolbox. So I think you all attended Dr. Ritojit sessions, right? And other Qiskit sessions, right? and you must install the software. If you haven't installed it, please install it with this command pip install qiskit. And there are some more packages, but at least you install pip install qiskit, okay, and then you continue. And if you have missed some other packages, if something is said it is not available, just type pip install that particular package, it will install, right? So now if I want to measure it, the protocol is my circuit name, and I want to measure this, and I want to measure the quantum register. EBIT 0 means Alice qubit, and I store in the classical register A, okay? And then I do protocol dot measure of the qubit q qubit, okay, and I store in the classical information B. These two measurement I do, and Alice does the measurement of E bit 0 means Alice qubit as well as the additional qubit Q, and stores the information in A and B. And then again I do the protocol dot barrier, and I do the barrier as well as I can see the protocol dot draw MPL. So now you can see, okay, let me share the code first. The code I'm writing, I'm also sharing in the chat box, right? Um, yeah, thank you, Professor Satish. Sir, you're sharing the requirement TXT, right? That's good. Now you can see the circuit. So first you prepared the shared entangled EBIT. Then you created between the information stored in the additional registers Q that you need to transfer from Q to Alice to Bob, right? There you are preparing the CNOT gate and the Hadamard performance, then Hadamard operations, and then you are doing the measurement on this qubit and this qubit, and you are storing these informations to A, and you are storing the informations to B, right? Now, based on the information of A and B, now B will do certain operations, right? Bob will do certain operations. So what are the operations that B will do? Bob will perform quantum operations based on A and B, right? So what are the operations that Bob will do? First is with protocol dot if test if test A is 1, right? Conditional if test. Then with protocol dot if test A equals to 1 colon, then protocol will apply x to the E bit 1, right? Protocol will apply X gate on E bit 1, and with the protocol dot if test B comma 1, if B is equals to 1, then protocol dot it will apply G to E bit 1, right? E bit 1. And then if the performance is done, then we need to display the protocol dot draw, and I can draw the output. equals to MPL. Now you can see. Now, okay, let me share the code for this part. So what I have done is the conditional statement I have done, right? That means if A equals to 1, it does the X operation. If B equals to 1, it does the G operation. And you can see conditional X gate and conditional G gate applied in B, conditioning on A and B like this, right? Now, suppose I define some unitary gate like this. Suppose I define some random gate equals to U gate. This is the way we define U gate. Okay, this way that we define some theta random dot random. So this is I'm calling from numpy library random, right? np dot you can also call numpy dot random or random dot random into 2 pi. You can take some random value into 2 pi as your angle, initial angle. You can precisely define the angle also like 30° in radian and all. Then comma. Second is I give some theta and give some pi random dot random. I can do it with 2 pi to into pi. And then I keep some lambda also. So this is a gate that requires 3 angle. Okay. Lambda equals to random dot random into 2 pi. Maybe in your code indentation error or some error, you just please check with the line of the code. Some spacing error is probably there in your code. Just it's a easy testing you can do. Why is showing double lines in that black dots? Can we consider it as a control point? Please show the circuit once also. Sure. Yeah. So this is just a conditional, right? And the double wiring is the classical interface, you can say, right? So operation on B performs X or not depending on the values of A and B. That's why it's a conditional check with the double lines and dot, right? So this is not a physical connection, but this is a conditional operations, right? Yeah, you can consider as a control point. Correct. So now once you do this some random unitary gate you design, and then you display suppose this array to latex just to see what is your matrix. Array to latex, and this latex will prepare the random unitary gate, right? Random gate dot to matrix u get is not defined. Okay, I called the u get, right? Some initially somewhere. Mm, mm. So let me check. There is some error. Mm. Yeah, G is capital letter, correct. Where you can see. Oh, correct, correct. Thank you for letting me know. You get you should be in capital letter. Yeah. So we define some random matrix like this, right? And once we prepare this random matrix, the circuit makes a few features of Qiskit that we haven't in previous relations. So the circuit initializes AB in the entangled state. So initially, where we are presently, let's check. So first we prepare the states, then we prepare this conditional NOT gate operations. Each operations performs measurement. Measurement gives some classical value A and B. Depending A and B values, we apply X or G operations on B to retrieve the quantum state that was there in the qubit cube, right? And now we choose a random unitary matrix, right? And suppose we apply this random unitary matrix just after this particular thing. So just let me share this part of the code first. You can please copy from the chat box if you are stuck in the code. And then our purpose is to just apply this circuit, you get circuit in. So just for the testing purpose, we apply this U gate right in the circuit and we'll do the measurement. So it's something like this. So up to this, we have something like this, and then we prepare another unitary gate that you get just we have done here. And then basically we do a testing performance with this U gate. So we apply the U gate here, right? And we'll do the measurement. So once we do the measurement, and let us see the results. So this part of the code I am not writing just to save some time. So this is just very standard way of writing it. So what it is doing, just to see. Okay, let me. Mm. So okay, so basically, we created a test circuit with qubit, ebit, ebit, A and B, and then we append the random gate qubit in the original circuit, and we put a barrier. We compose. Okay, test.compose protocol. It just compose it, and then barrier, and then basically do the measurement and testing. Just drawing these things. Now, once you see the results, then you can understand how it works. So result equals to, suppose we simulate this circuit on a quantum simulator. Uh, Qiskit has the ER simulator, and we run the circuit, run the test circuit, right? Not the original one, test circuit, and then we find the result with the result function. So first, there is a test circuit. We run the test circuit, and the result of the test circuit is done with the ER simulator. So this is just the format of writing. And then once you do that, then we can find the statistics, that is equals to result dot get counts, get counts. So we can find that after how many after certain iterations. So what is my probabilistic result, right? So I can display now the histogram. So I can display now plot histogram of the statistics. So now you can see I have to minimize the size, otherwise it is not visible. Yeah. So, okay, let me give you this part of the code, MPL regions. And so now you can see that the original state, right? That was the state that we prepared, right? Almost in the superpositions of 1/4 probability that we have seen, right? And because of certain errors, the count is roughly coming every values out of, say, 1,000 measurements, each particular quantum state 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, and 0, 1, 1. They're coming roughly approximately 1/4 as the probability. Okay, so nobody will have the same probability. Okay, because you created a different unitary gate, right? You get with random values, and also quantum measurement does not give you the exact result, it's the probabilistic result. So roughly approximately 1 by 4 is the probability, but it should not be same. Okay, you might have a different name because you have a different u gate also. U is preparing with a random gate, as well as there are errors, right? So and that will come into picture. So now if you put this particular setup, maybe this particular code, maybe then you will see a marginal probability distributions, right? So this is not that important, just marginal distribution you can plot, but this is optional. It's not that required. This is an optional, just a marginal distribution for the state zero, right? Um, So with this, I conclude the session here today, and please feel free to put questions. All the code lines I have given in the chat box. Those who could not complete, please take the code lines from chat box, and the notes that I just covered, I'll share it with Professor Pillai sir, hopefully by today. And if you have any questions, please feel free to ask me in the chat box. Yes, sir.
Right, sir. Marathon. Marathon
Very
completed.
sorry, I took a lot of time.
No, no,
So
we are very much in right.
yeah, so what I did, sir, the topics that I taught in the MNIT series, right? I
Right.
I copied your YouTube link and put in my website 1, 2, 3, 4, sharing the link so that they can at least see my lectures. Okay.
करेक्ट अच्छा ये वाला डायरेक्ट हाँ हाँ नहीं बिल्कुल ठीक है कोई नो प्रॉब्लम
With your
एब्सोल्युटली
kind permission.
अरे नहीं
Okay.
आपने परमिशन दिया हमको यूट्यूब पे रखने के लिए
Yeah.
that is actually that is so nice of you. Some all the teachers have permitted that we use. Yesterday also I was talking. Then some of them did not know about the MNIT series. So Delhi में कोई college में lecture ले रहा था. So they immediately they said sir वो links बताओ. Then I showed them on YouTube. They were
Yes.
surprised. "अरे sir इतने सारे material है." And I said most of them are IBM professionals and they have contributed a lot. तो आप सबके रख दीजिए उसमें है ना जो भी लेक्चर नंबर डाल दीजिए डेट्स इन दैट आई थिंक
Yes.
यू वुड हैव पुट दैट आल्सो राइट
Yeah, I only copied the links for my topics and
राइट दैट्स
put
फाइन हाँ फिर
yes,
तो ठीक
yes. So quantum computing, quantum communication, and all. So probably
राइट
some are missing. I'll do it later, but most of
राइट
the
राइट
thing that yeah.
ढूंढ लेंगे बाद में वहां से
Yes, yes, yes.
या Yeah, I think only the thank yous will be there. No questions. Already questions are cleared, I
Yes.
think. Yeah, if there are any questions, participants, please, you can ask Dr. Mustafizur is there. We have another 2-3 minutes if you feel. Uh, Kindly note, quiz will start. Yes, sir, cleared already. Yes, I think. So we will have the quiz starting today. Quiz 3 will be starting. So I'm trying to get the notes of Professor Kallol Bhattacharya sir. But in case we don't get it, you can follow it from the what do you say the YouTube lectures and then prepare for. There may be 3 or 4 questions from his notes. So please go through the material and then do the exam. So I think that's the best that we can suggest for you. But remaining material, everything is already there. Sir is already going to share, and we will put that material also online immediately, and we will have it. So in that sense, a large amount of content was covered, and hence because we want you to read sir's material, we have kept sir's content also in the quiz. So we you can please note that the quiz exams are till today's lecture, right? Contents will be based on today's lecture also. So quiz questions have been given. So please understand that quiz 2 we are opening for those who have not taken it even one time. So quiz 2 will be open till Monday evening. Quiz 3 will be open till Tuesday evening. Quiz 3, quiz 2 both will open today evening 6:30. Both quizzes you can take immediately and then you can take the exam. But then but this will be the last attempt for quiz 2. We will not open quiz 2 later. So already 800 plus have taken. About 100 people are here to take. So 100 people should take that exam, and quiz 2 we will close. So 900 plus have cleared quiz 1, quiz 2 900 plus will clear. Quiz 3 also please complete before Tuesday. We will try to award the certificates by next Monday. So that is the 25th, 30th of November, 31st. Continuing Saturday, Sunday, na? First December, we'll try to issue the certificates. Please note, 8th December, the next course, quantum computation, is starting. Please be prepared. We will share the folder today. 1st December, we'll issue the certificates. No more extensions for any quizzes. So please complete quiz 2 and quiz 3. Quiz 3 you should complete by Tuesday, that is 25th. Quiz 2 you must complete by 24th. Right? All YouTube videos will not be deleted. They will always be available. Even from QT-01, the course is available. So you can, of the amenity series also is available. Please, you can make use of that. We'll try to keep the Canvas material also ready, be available for more time till December 31st. I've extended, but we don't know when Canvas may restrict us. So please download the content and keep it with you. That's what I would suggest. So please do it at the earliest, right? With this, I want to also remind that tomorrow there is no class. Tomorrow is Sunday. So please
Thank you.
don't message me at 3 o'clock that there is no, sir, link has not started, right? We will meet on Monday at 3 o'clock. We will start with, I think, industry lecture will be there on that day. Ashwath sir will be taking the slight change. Ashwath will be taking on 25th and 26th. On 24th, we'll have some industry expert taking. We will announce in the group, right? So thank you so much. Thank you, Dr. Mustafizur, for your 10 lectures, and thank you for sparing the valuable time. Right? Thanks, sir.
Thank you so much for the invitation.
Right. We'll meet on 10th December.
Yeah, sure, sir. Yeah, thank you.